Hello everybody, my name is Tom McCormack. I would like to welcome you to today's presentation, Are We Stardust? Of Christoph Mayer, who joined us from the University of Heidelberg. This is a hybrid talk, so we're streaming it to the internet, and Christoph is also live at the SFN in Kassel. And on the bottom right of your screen, you can see raise the hand button, and if you have any questions, you can just press it and write it into the chat, and I will try to ask the question to Christoph for you. I think that's everything I'm going to say, and now I'll just pass it to Christoph. Thank you very much for doing the talk.
Yes, thank you very much for your invitation. Today, I would like to invite you to my talk. So, today I would like to invite you to my talk about the question, are we stardust? Well, a lot of persons test.
We're just solving some technical issues.
Okay. Always a little bit of technical problems, but let's just start. Well, the question that's always asked is, what are we here for? What is the reason? What should we do as people? And also, what makes us people? And today I would like to talk to you about, are we stardust? And if we are stardust, how have we been created and how did everything happen? So I'd like to invite you to a journey through time and space, from the beginning, the so-called Big Bang, until today. And well, in the Bible it says, in the beginning was God, and God created the earth and the heavens. And in another verse of the Bible it says, in the beginning was the Word, and the Word was God, and so on. But I didn't want to talk about the Bible today. The thing I want to talk about is, what does science say about the beginning? And it just can't say anything about it, because we cannot really say what the beginning exactly was. We cannot fix a beginning. We cannot fix a time where we say this is second zero, because there's yet no theory that can describe what has been before a so-called Planck time. The Planck time is a really small fraction of a second. And this really small fraction of a second is the first thing we can extrapolate to, or science can extrapolate to, and say, okay, from this point on, we can describe what we know. What's been before, maybe a singularity, cannot really be fixed. The reason is, the general relativity theory does not allow a singularity in the beginning of the universe. But if there hasn't been a singularity with all masses and all energy, what could have been there? One just doesn't know. Quantum gravitation is one theory that may describe it, but you don't really know. The idea is that maybe there could have been some kind of great force. In German, you would say Urkraft. And this great force, that should have split up later into gravity, electromagnetic force, and the atomic forces, the strong and the weak. but you just don't really know. So let's talk and let's begin with the Planck time and what has been there. At the Planck time, we've seen a great expansion of the universe. This is called inflation. And this so-called inflation made something that was a lot less big than a proton to about 10 centimeters. Well, because this is just extremely hard to imagine, let's imagine that a proton, that I think no one of you has ever seen, but let's just say a proton, it's extremely small, expanded to the distance between Earth and the Sun in a fraction of a second. This is called inflation, and this is why some people imagine the Big Bang really as an explosion, because it was just everything was there. So before there really was no universe that our universe could expand in, no space, no time. This is hard to imagine, but let's say now we can go into the universe. And now we can really look what is in the universe. Before we had to look from outside, but no one knows what outside is. And well, if I would dim the lights here now, you maybe would feel how it's been in the universe. Because in the universe at that time, it was just dark. There was so much matter. It was the universe was filled with everything of gluon plasma and quarks, the smallest particles we know of, the smallest particles that made up protons, neutrons, and so on. And it was just filled with this. And no light could pass through this dense medium, so it was just dark. There was nothing to see. And it was so hot that nothing could have survived this. But then the universe cooled down. It expanded, and with the expansion, it cooled down always. And by cooling down, it enabled the nucleosynthesis to work out. Because then, the first time the quarks were pulled together by the weak and by the strong force and formed the first protons, formed the first neutrons. And these then collided with other quarks, with other elementary particles, and so on. And through these collisions, the first elementary cores were formed. Here we can see how deuterium was formed. This is heavy hydrogen. So normal hydrogen has one proton, one electron. Deuterium has one proton, one neutron, and one electron. And these were the cores. And when these again collided, the first helium was formed. And by this, there was an emission of light. That's the reason why this slide is gray, because there was a little bit to see, but the light could not go any further than just a few, just a fraction of a meter. And by this, the first elements were formed. Hydrogen and helium. Hydrogen formed as 75% of these nucleosynthesis reactions, helium 24%. Now you may ask, what were the 1% that was left? This was lithium, beryllium, and so on. The so-called, in astrophysics, well, every chemist would kill me, but in astrophysics, it's called all metals. Everything that's heavier than helium is a metal, because it was not really formed in the nucleosynthesis process of the universe in the beginning. And after these cores merged the first time, there came a very interesting time. This was the time of recombination. In the time of recombination, the electrons in the cooling universe were able to couple the first time with their atomic cores, and therefore create the first atoms we know today, not just their cores. By this, the universe became transparent because there was less matter that was just floating around, but more bigger gas clouds and so on that were formed. And from this first emerging light, this first transparent universe, we can measure today this picture. This is the so-called cosmic microwave background. This is the first thing that we can see in the universe. So if you would zoom out on a space map, you could see stars, galaxies, and then bigger structures like voids and so on. And if you zoom out enough, you could see this cosmic microwave background that is everywhere in our universe, even today, and that was measured extremely sensitive. These small differences in temperature and density are the reason why we have large inhomogeneous structures all over the universe today. Maybe some of you know the word void or big galaxy clusters and so on. These were formed by this. These fluctuations that spin there are the reasons why then higher density, more gravity, everything came together at this place, and nothing came together at this place, or less. I will go to this in a second, but at first, it was again dark after this. Because after the first light could pass everywhere through this and created the cosmic microwave background, it was again dark. And the reason why it was dark is just because there was nothing that could emit light anymore. The atoms have been produced. They were in large gas clouds everywhere in the universe, but there was no star or something like this that could have emitted any light. These cooling gas clouds then, under the influence of gravity, came together and have born the first stars. We can see this here in the Orion nebula. In the Orion nebula, of course, is something we can see today, not any cloud that have been there these billions of years ago. But this is the star-forming region. The same principle, for the same principle as billions of years ago, the first gas clouds formed the first stars. In this Orion nebula, now gas clouds form the stars. Because stars are nothing more than open systems of a massive amount of gas. I will come to this in a second. And it is yet unresolved if also the first black holes have been born in these large gas clouds. Because if a star is formed by a lot of gas, and a black hole is nothing really more than a star that, let's say, exploded or imploded, that just collapsed, then these extremely large gas clouds also could have collapsed to primordial black holes. Primordial black holes could have been playing an extremely big role in the creation of our universe, in the creation of galaxies and so on. Because maybe the first supermassive black holes that are the core of, let's say, every galaxy could have been formed like this. But also small black holes, like the theory of planet 9 in our own solar system, could have been formed at this time, primordial. Others say, no, black holes could only have been formed by exploding stars and then afterwards more and more accretion. Maybe it was both. We don't really know it yet. What we know is how a star is created, how it evolves. And when we look at these large gas clouds, where all this gas comes together and is pulled together, we have a lot of gravitational pressure. And the star is an open system. So there's gas outwards flowing in due to gravity, and due to pressure, gas wants to go out. And with this, there is a stable equilibrium where some size of the star is, where some size of the star exists, and the rest of the gas is just blown away of the gas cloud. And then something very interesting happens, because due to the gravity and due to the extremely high pressure at the core of the star, new elements can be formed by so-called fusion. Because let's just imagine the first stars have been made up of hydrogen and helium, the things that were created in the nucleosynthesis process. Then this big pressure forced the helium and the hydrogen, due to their lower binding energy, to build up more and more elements, heavier elements, because their cores were just smashed, and with their smashed cores, they had then lower potential energy, and how chemists would know, lower potential energy means a more likely state of an atom or something like this. So by smashing these cores together and forming chromium, carbon, oxygen, neon, magnesium, up to iron, we get energy. This is the reason why we try to have fusion plants, and why we try to use the sun's energy, the warmth and the light, because it was just made by smashing some atoms together. And then in the stars, during their evolution, these heavier elements form like an onion shell. You can see this here. And this onion shell has some, let's say, has some time to die. And when it dies, something interesting happens. On this so-called main sequence, helium is being fused by smashing hydrogen together. Afterwards, the heavier elements are being fused. The normal main sequence star becomes a giant and then a supergiant. So it blows up. Its shell just blows up because there's so much pressure in it, so much energy that it wants to flow out. And at some point, the iron core just gets too heavy. And when the iron core gets too heavy, something interesting happens, because it just reacts and we get a great supernova. One of the most energetic explosions we know of yet. This is supernova lets the whole star and the whole shell we've once had explode to this kind of nebula, the supernova remnant. And the supernova remnant is then full of all these elements. It is full of hydrogen, helium, iron, and so on. But this supernova remnant can then be recycled again. Can be recycled again to a new star-forming region, like the Orion Nebula. And then it forms a new star. And this new star has new heavier elements. And then this new star lives again, or maybe a lot of stars, because the first stars were extremely big. Maybe a lot of stars are formed in this and build up an open or closed cluster. That could happen. And that's the reason why all elements are being formed in stars by exploding stars or larger events. Well, what do I mean with larger events? At first, there were stars and maybe also primordial black holes. But those of you that are interested in astronomy, astrophysics, and so on know that there are also neutron stars and so on that were not normal stars, really, but that have high mass, some kind of remnants, and so on. And we can then see the origin of all the solar system elements, all elements we yet know of. Hydrogen and helium have mostly been formed by Big Bang fusion. That's the nucleosynthesis I've told you about. Helium also comes from exploding massive stars and dying low mass stars, because it was in the beginning fused by these main sequence stars to get their energy from. And then we can see lithium, beryllium, bromium, carbon, nitrogen, and so on. Some also dying low mass stars, some exploding massive stars. Beryllium, bromium cannot be created by fusion, but can be created by cosmic ray fission, because the potential energy by let's say fusing lithium and hydrogen to beryllium or something like this is nothing you can get energy from, because the potential energy is higher. And therefore you get energy by destroying the core again. And this can happen by, let's say, gamma ray photons, so high energetic light, and that's how these were created. Exploding white dwarfs, this is some kind of supernova again, because white dwarfs are, let's say, a kind of star. And something that's also very interesting, what we've just measured, I think in 2018. I think it was 2018, by gravitational wave detectors, are merging neutron stars. Because two merging neutron stars also explode extremely strong. And then all of these very high mass and very heavy elements can be formed by this large event. And then going on, these elements are being formed, and then the large clouds all come together over billions of years. And by this, larger structures, not only stars, but larger structures like galaxies for example, are being formed. And what we know today is that in most of those galaxies, a so-called supermassive black hole of millions of solar masses must keep the galaxy together, because we found so-called accreting black holes. This is the Hercules A galaxy, and what we can see here are the jets. This is the galaxy. This is a whole big galaxy. And these jets are so massive and so big, you just cannot really imagine how big they are. But when a supermassive black hole eats up stars, eats up maybe other black holes, then some energy has to flows out again. And this outflowing energy goes exactly in two directions. You must imagine you have this supermassive black hole. Around this black hole is a so-called accretion disk. That's in this plane. And perpendicular to this plane, two jets emerge from the black hole that are extremely energetic and go this far. These are light years. These jets go. And then maybe sometime in our galaxy could have been that our supermassive black hole then relaxed and says, okay, now I cannot accrete anything more or not as much to build up these jets, these highly energetic jets. And then our galaxy could have been created by this. And in such a galaxy, our solar system then had formed. Here's the example of H.L. Tauri, where we can see in the middle the star, and around the star a so-called protoplanetary disk. This protoplanetary disk is made up of stones. It is made up of gas. It is made up of ice and everything. And then, due to the gravity, we always get like the same structure. Closest to the stars, we have a lot of stone planets, like Venus, Earth. And then if we go Mars, and then if we go out, we get gas planets like Jupiter, gas giants. And if we go out further, we get ice planets. Neptune, for example, is a gas and ice planet. It's extremely cold, and just through gravity and maybe larger objects that are traveling through this protoplanetary disk, all planets emerge. And that's the reason why our solar system looks exactly like this. We have this large ball of gas in the middle that's burning and giving us our energy. Around we have stone planets, gas planets, ice planets. Some of them have moons, some of them have not just one moon, but a lot of moons. And yeah, the solar system with Earth then was finished. The rest, history. Because after that, the oceans formed, life came to the Earth, it evolved, and so on. But I don't want to talk about this now. The thing I want to conclude with is we emerged from like nothing. We cannot really say what it was, maybe a singularity whatsoever, but we emerged from nothing. And all elements we are made of, carbon, iron in our blood, and so on. Everything you can see around you, just look around you, is the same. I'm really nothing more than this table or this computer, because everything is just an exploding star. Everything is just stellar dust. And this stellar dust was created somewhere here at the first stars, and this is where we all come from. And that's why it is extremely interesting for me to have a look at how the Big Bang was, how the inflation happened, and how the universe expands, and so on. And this is also what I am writing my bachelor thesis about at the moment. But this is the thought I would like to let you out today. Maybe you can think about it a little bit. If you drive in your car and then someone stops you and you just want to say, I hate you, just don't do it. We're all stellar dust, nothing more. Thank you. I am open for questions.
If there are any questions from the online audience, just feel free to write them down in the chat. Okay, so no one's writing. Then at first I would like to thank you very much for this very interesting talk and giving us good insight why we are all stellar dust. I think it was a really informative talk. And if there's nothing else, I will close the room soon. Thank you.